Hi there, crowd.
Hey, hello. Can you hear me okay?
Yeah, your audio's a little bit low, but I hear you okay.
Okay, so the other day there was, oh, let me fix this. I cannot hear
I
myself.
got you. It was on my end. My speaker was down. You're fine.
Okay, so the other day there was some discussion about Coriolis effect, and I found that even some Globers they confuse some things or they don't have answers for some things. So
Yeah. Well, the
I
thing is, the whole subject of Coriolis in general is a very complex, complicated subject. Even a lot of engineering students get it wrong. Um, this was discussed extensively back in my university days in a engineering dynamics course where we're dealing with the kinematics of rigid bodies and um, the Coriolis force and effects that you hear discussed in a lot of these hangouts like Nathan's and in discords and stuff. It's just a very fundamental simplistic aspect of Coriolis. Coriolis can get very, very complicated when you have uh, rotating frames within rotating frames. It doesn't involve just two frames of reference, like is a lot of people are contending that you have a linear non-rotating frame or an object moving in a linear direction in a straight line in one rotating in one frame, and then you have a rotating frame and you see the apparent deflection. That's a very basic fundamental nature of Coriolis, but you can have more than two frames of reference, which of course people like that don't understand it, like Nathan and Quantum Eraser has time and again tried to roast me on, but they don't understand the general form of Coriolis and how it can come into play. But go ahead. I imagine it's just the fundamental aspect of a linear trajectory of an object as viewed from a rotating frame that you're probably going to discuss here. Is that correct?
um I'm not sure because I watched that Nathan show when you were talking about this Coriolis. I think I was there watching, and the
Well, that
problem
that
my
show was
personal
that show was a
but
disaster because they cut out most of my audio and never let me really explain it. The minute I brought up more than two frames of reference, Nathan just went ballistic because he doesn't understand the nature of how more than two frames of reference can come into play. But anyway, go ahead.
it was a big problem for me because once you started to say frame of reference, I myself felt lost, and when Nathan brought a lot of bullshit, I was more lost. So I have an issue with scientific terms. So
Okay. Well, first, uh, maybe I can interject here. Do you mind if
yes.
I let me explain what a frame of reference is? Um, the way Nathan and Riley and all them describe frames of reference is wrong. They sort of think it's like some physical entity or some physical realm, and it doesn't have to be. Frames of reference can be purely imaginary. Frames of reference is a coordinate system that you attach to an observer, and the observer can be in multiple plane spots. Like on the Earth, you can have an infinite number of reference frames. You can attach a reference frame to each or a coordinate system to each air molecule. You could attach it to a car. You can attach it to a bicyclist. A frame of reference doesn't have to be a physical realm. It's a spot in which you place an observer, and that observer is going to make measurements and observations and describe to you what he sees. That's what we mean by a frame of reference. Also, a frame of reference can be applied and attached to objects like a ball in flight or a bullet in flight or a plane in flight. It can be attached to objects, but it doesn't have to be. It can be purely an imaginary or a place in space from which an observation is going to be made. That's what we mean by frames of reference. It's just where you place an observer and you attach a coordinate system to observers, because that's the only way we can really measure things. You have to have a reference. You have to have a origin to your coordinate system. Like you go into a town, you have a grid system that's usually set up on streets and avenues. You can have a central point from which they start. Loveland, Colorado, where I was at, there was one place downtown where you had First Street and First Avenue, and everything measures out from there, so you know where you are relative to the center of the town. That is a coordinate system. So in order to describe analytically what is happening, you have to have some sort of a coordinate system by which you can measure distances and positions. And that's all a reference frame is. You attach a coordinate system to a place where the observer is, from which he can make his measurements to describe what he observes, to describe with measurements analytically. I don't know, does that help you?
Okay, let me tell you what I understand, or put an example to my understanding now. Like if we are shooting a bullet from the North Pole and it's going to land, or supposed to be heading towards London, there is a frame of reference for the North Pole, and London is another frame of reference.
Well, yeah, if you're going to put your observer there, or you could put an observer in the United States. There's a third frame of reference. There's an infinite number of frames of reference that you can choose from. Just depends upon where you want to place your observer in order to describe what he sees.
Okay, so I, I think I should start sharing my screen and uh, tell you my understanding, and maybe we can refine it.
Sure, sure.
Yeah. So I'll share my screen.
But there's nothing sacred about any particular frame of reference. Now we have kind of like when you start getting into relativity theory and all this sort of things, we have specific frames of reference that we talk about. Most of the time, we're talking about what Einstein described as inertial frames of reference. That is, frames of reference that are moving at a constant velocity in a straight line with respect to one another. No acceleration is allowed in these types of frames, which we call inertial frames of reference, and then you can make use of what's called the Galilean type transformations. That is, positions relative to these types of frames are just linear relationships that involve the velocity that is relative between these two frames of reference. And then you have accelerated frames of reference, which are characteristic of rotating frames. A rotating frame always has acceleration. So a rotating frame of reference, for example, wouldn't be covered under special relativity, because special relativity only involves inertial frames of reference. That is, frames of reference that aren't accelerating.
Okay.
Okay,
That
let me.
that's my.
I'm sorry, I'm in the wrong place here. I was on
No,
Skype.
no, no. It's okay.
Okay,
But
I've got your screen now. Go ahead.
you reminded me now of one of the paradoxes that are not that much covered online. I just found it by accident, and it's not there a lot. I cannot remember the man's name, but he said if a disk is rotating, something like that, so there should be length contraction, so the disk will be. Did you
Well,
hear about
see,
that?
a rotating disk is not covered under special relativity.
Okay. Okay. So I'll share my screen. So
I don't.
can you see it
Okay.
now?
Yeah, I got it now.
Okay, so I started from this simple diagram, this appears to be a circle, but it's the globe, and this is the North Pole.
Okay. Yeah, and
So,
it's rotating west to east, counterclockwise. Fine.
yeah, yeah, okay. So if I have three targets here at different ranges, and
Yep.
there's a constant spin, like
Yeah, we call it uniform circular motion.
okay,
Everything's rotating at the same omega. Omega is rotations per second or measured in radians per second. It's called angular velocity, and it's constant for every point on a rotating Earth. It has the same omega. Now, angular velocity is not the same as linear velocity. The relationship there is if you measure the distance outward from the North Pole, then the linear tangential velocity associated or the lateral velocity of an object is omega times r, the radial distance out from the North Pole. The omega is constant. The angular velocity is constant for everybody on the Earth, but the linear lateral component to the velocity is not, which, flat earthers always like to quote the tangential velocity at the
thousand.
equator, which is 1,035 miles per hour. That's linear tangential velocity. That is not angular velocity.
Yeah, so I think that you see the red bars, vertical bars.
Mm-hmm.
This
Yeah,
after 1 second. So I think this is,
that's representing the tangential velocity magnitude, I would assume.
yes. So if I have the tangential velocity and I have the time, I can know what the amount of shift from how much the target moved away from the direction where I was looking at it initially.
Well, only the horizontal or in this case, the vertical component to it. I mean, no, the actual movement is omega times r times time, which is your. I'm splitting hairs here. Because I want to make sure you understand the concepts. Is the arc length that it's moved along the arc is just the radial distance times the angular shift in
Yeah, with a
radians.
sine and cosine.
Well, no, you don't have to use sines and cosines. It's just omega times r. Um, the and the omega is a time derivative of the angular position theta. See, if you draw a radial line horizontally from the North Pole out through the three bottom targets, let's take that as our reference, our horizontal reference, okay? We'll say that's at 0 degrees. We're measuring counterclockwise, and then if you were to draw a line from the North Pole through the three upper targets and measured the angular distance, angular measure, the angle between the lower targets and the topper targets, we call that, say, angle theta. That's some angle measurement. And if that's measured in radians and you multiply by the radial distance out, then that tells you the length of that arc between any of the two targets there on a constant distance around. Do you see what I'm talking about there?
Yeah, but that arc will be virtually a straight line because I'm dealing with like,
Well, if it's short enough, if the
yeah,
angle theta is small enough.
yeah.
Yes.
So this example here is exaggerating because this is
Right.
like
Yeah. So
hours.
yeah, I mean, as long as your angle is say under about 5 degrees or so, the error in arc length compared to the straight line distance is negligible. You don't have to worry about it that much.
Yeah, I counted on that. So I can get the tangential velocity according to the
Right.
latitude line.
And you multiply by time and you get the distance. Yeah.
Yeah.
Okay.
But first of all, if there's no atmosphere, then we can apply these equations simply. But the
Yeah. So
problem
if
is,
you neglect atmosphere, just say that your objects that you're dealing with have very little aerodynamic drag. So essentially, it's like operating in a vacuum or without an atmosphere.
okay. So now my bullet for this target, it will reach to this location when the target is here. You're with me? When the first target at position 1, my bullet would be here and the target would be here.
Now, are you going to be talking about the same intervals of time in each case here then?
Yeah, I'll just talk about the first case after 1 second.
Yeah, so we're dealing with a uniform interval of time in each case. Yeah, so in the first position, yeah, it'll move a certain distance, and then as you move out further from the North Pole, it'll travel a greater distance because the tangential velocity is larger as you move closer to the equator away from the poles.
Yes, but now I'll be talking about only these two, the first
Okay,
position and
go
after
ahead.
1 second. So, but as the bullet is traveling into that direction, the atmosphere is rotating with the Earth and wanting to push it with the direction of the Earth.
Just a second. I just got a message from Rumpus here. Hang on. Okay. Sorry. Okay. Now the atmosphere is going to do what for you?
The atmosphere is rotating with the same speed of the Earth, so
Yeah,
it
the
will be
surface of the Earth
wanting.
and the atmosphere as a whole is rotating
It,
at the same rate. Yeah. Yes.
and so it will be wanting to push the bullet into that direction.
No. No. All right. Go ahead. Say what you're going to say. All right. Go ahead. Go ahead. Go
Okay,
through. I won't interrupt, and then
so
I'll tell you where it's all buggered up. Okay.
so
Has
okay,
nothing to
so
do
this
with
is the
the
first
atmosphere wanting to push things. But go ahead.
sheet or first spreadsheet. I put the what?
I say all of this has nothing to do with the atmosphere wanting to push bullets or objects, but go ahead.
Okay, so we'll discuss this first. It has nothing to do with the atmosphere. So I put the latitude line of the starting point and the average horizontal speed of the projectile and the range, and
Okay, here, hang on a second. Hang on a
also
second.
the direction
Hang on a second. I'm going to get my
90 degrees
calculator out.
from east. So that would be exact.
Yeah, hold on. I get my calculator out so I can verify your numbers. In anything like this, you should probably up near the top, right? At the very beginning, state what the omega of the Earth is. I'll tell you what that is. Um, the Earth turns 2 pi radians in one sidereal day, which is close to 24 hours, but I'll use the exact, which is 23 hours, 56 minutes, and 4 seconds. So that's 86,164 seconds. That's the period in one day, or not in one day, but the time for the Earth to rotate in one revolution. That's a good number to know. It's 86,164 seconds. So if you divide that into 2 pi, your angular velocity of the Earth is 7.388 microradians per second. So hang on here a sec. So if I take that and I multiply by, you say you're at 89 degrees, so you're about, what are your units? I don't see your units here. What's that, 500 meters per second? Oh, okay, meters per second. Okay, I see it now.
It was here, but because I wanted to show some columns here.
Yeah.
Just to
So,
show
all
you
right.
what.
So for each degree, you're going to be out, let's see, we've got about 10 million meters from the pole. Well, I'll do it exactly here. Let's use, what are you using for radius of the Earth? 6,371 kilometers.
Yeah, that's what I did.
Okay. Here, let me write all this stuff down. I just want to, I don't mean to be sidetracking you here, but I want to verify things. I never ever
Yes.
trust anybody
Yes, that's correct.
because it's easy to make errors. So our omega is 7.3885 microradians per second. Radius of the Earth is 6,371 kilometers. Now, to compute your lateral velocity, you have to take the distance from the axis of the Earth out to the surface, which is not the same as the radial radius at any given point. So what you have to do in that case is find the horizontal component, and you take the latitude, which I'll call theta L, your latitude times the cosine,
Of the
or
Earth's radius.
the cosine of theta L times the radius of the Earth gives you the radial line that you use for computing the tangential velocity. So your tangential velocity will be radius of the Earth times the cosine of your latitude angle times the omega of the Earth. So in this case, we can take the tangential velocity at the equator will be the radius of the Earth times the angular velocity of the Earth. So if oh, the hell did I do there? E3 divide. Okay, so we've got 6,371 meters times the omega. So the tangential radial velocity is 470.7. Oh, no. Sorry. 47.072 meters per second at the equator. Does that work out right?
Say again, how many meters per second?
47.072 meters per second at the equator.
I calculated at 463 meters per second.
Okay, I might have. Let me just check something here real quick again. I'm sorry, my head is swimming right now. It's not doing very well.
That's okay.
6371000 multiply. No, I get 47. Let me divide by E3 divide, multiply by 3,600 to get kilometers per hour. Yeah, you're right. Why am I coming out wrong here? I'm coming off by a factor of 10. I must have computed the omega wrong. Let me do that again. Period of time is 86,000. Oh, I'm sorry that I'm delaying things here for you.
Take your time. I'm all free and just like to get to the bottom of this thing.
Um, okay, so the period of the Earth is 86,164 seconds. And if I have 2 pi, oh, okay, that's where it is. I'm sorry. The omega of the Earth is 72.92 microradians per second. I was wrong. I must have hit a wrong key. I do that often. Okay, so we've got 7. I'm just going to re-verify that here just to make sure. 2.141564 divide. Yeah. All right, so the angular velocity of the Earth is 72.92 microradians per second. Radius of the Earth is 6,371 kilometers. So the tangential velocity at the equator would be the radius of the Earth times the angular velocity of the Earth, which we would take 3,300 or 6,371 kilometers times the omega of the Earth. And to put it in meters, we take 6,371,000,000 meters times 72.92 microradians per second. So the tangential velocity at the equator is 464.6 meters per second is what I get. What did you have?
I'm sure I had different because I used the pi as 22 divide 7, not the exact pi.
Oh yeah,
So
that's off by quite a bit. Yeah, I always use 3.14159.
just in my reading it 463 point say point 5.
Yeah,
So we
if you want a little better for a value you can use for pi rather than 22/7. If you want to use decimal, use 355 divided by 113. That will give you pi to about 6 decimal places.
yeah, that's too much accuracy for this. Maybe when we're launching Apollo 11, I would use this.
All right. Okay. So anyway, you had what for the tangential velocity at the equator?
463.5.
Oh, okay. Yeah, I mean we're within uh, a couple tenths of a percent of one another. Fine. That's fine. Okay, I'll agree with that. Now, to find the tangential velocity at any point on the Earth, we take that value and multiply by the cosine of the latitude at which you are at on the Earth. Okay?
Okay. So I
So,
have two latitudes here, the start point and the end point.
okay, so your start latitude is 89. So hang on a sec. I gotta make sure that I am in degrees right now. Okay. So if I multiply that value, I get 402.3 meters per second. That's at 89 degrees north latitude.
I think maybe it's sine, not cosine, because I get a very
Cosine.
small number.
Cosine.
But you're you-
Oh,
you're
wait,
you're
wait,
very
wait, 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 wait. No, you're right. Let me think here. Yeah, that's right. I did wrong. Yeah, cosine of 90 degrees is 0, so it's got to be a small number. I'm still waking up here. Okay, so I've got 464. I'm glad I have you to correct me here. Until I wake up, it's going to be a little bit rough.
it's okay.
So if I take 89 and I take the cosine of that, multiply, I get 8.11 roughly meters per second.
I get 8.089.
Yeah.
Start.
Okay. It's close. We're close. Your difference is, well, it should be in the ratio of our values. So if I take your value, if I take my 3.14159 divide by 22 multiplied by 7, the difference is 0.9996. So if I take my 8.81 multiplied by that correction factor, I get 8.10. Is that what you got?
8090. Wait a minute. Let me put the 4 decimals.
Well, no. I mean, I can't quite. What did you use? Okay. How did you compute your, what did you use for radius of the Earth and what did you use for the rotational period?
Rotational period exactly 24 hours.
Okay, well, that's where the difference is because the actual rotational period is the sidereal day, which is about 4 minutes less than that. So that would account for the difference. Okay.
Okay, let me use your equator speed.
My equator speed is 464.6 meters per second.
464.6.
Yeah.
0.6. Right, so I'll be using this value here and here. Yeah. Okay. So now these are the new numbers. Can you see them here? The start and
here. Just a second. I'm going to make sure that this is what accounts for the difference. .02, and then you had 8.11 divide over x. Yeah, that accounts for it. Is in the sidereal versus the solar day. Okay, so you have 89 lateral. You 464. Let me 14159 multiply 86164 divide. Okay, 7292 and 6371 123 multiply 464.6. Yeah. Okay. Fine. I just re-verified it.
okay, now that's the number that I'm using, and now I'm showing the start, the lateral speed at start point and the lateral speed at end point. Can you see them on the screen?
Lateral speed start 8 point. Yeah. Okay. I'll agree with that. I use 8.11, which is what you've got rounded upward. Okay. So if I take 89 multiplied by cosine, yeah, that's exactly it. 8.108 is fine. Yep.
Okay, now the end lateral velocity depends on the end latitude, which is this.
Okay.
And
Now let me take
this may
that.
not be very,
Say
okay.
what? Go ahead. What?
Okay, I got this end latitude based
You're
on that. What?
88.991.
Yeah, based
Okay.
on 111 kilometers for each latitude line. This is not very accurate.
Well, let me see here. Start, finish. The finish should be I get 8.180. Yeah. It should be 8.181.
Yeah, okay. I got that also.
Okay.
Uh,
Just take it to 4 significant figures.
like this?
8.181. That's
Yeah,
fine.
so
I mean,
okay.
you can take it to 4 decimals if you want, but it's unwarranted for the precision that you're using. 3 decimal places is what you should be at.
Like now?
Yeah. That's fine.
Okay.
Okay.
So now we have the difference. The difference of speed per second is 0.73 meters.
Now keep in mind, this is the lateral component of the velocity. Okay.
Yeah. Mhm.
Right.
And
Okay.
I'm shooting south.
That's correct. So as you shoot south, the Earth is speeding up underneath the bullet.
Yeah. So and then the range was 1 kilometer, and the average speed is 500 meters per second. So that's 2 seconds. Multiply by the shift per 1 second. I
Well,
get
okay. Well, keep in mind here that for different velocities, you have to do this a little bit differently because you're basically right here in what you're doing is you're shooting south. So keep in mind what's going on is that instant that bullet leaves the muzzle of your gun, it has the same tangential velocity as a starting point of 8.108 meters per second. It has that component and it doesn't lose that. It always has that same lateral velocity, whereas as it's moving to the south, the tangential velocity of the surface of the Earth is increasing because of the radial distance out from the North Pole, and that changes as the bullet is moving. That radial component under the Earth, lateral component of velocity is increasing and increasing. So relative to someone standing on the Earth, he is moving faster laterally than the bullet, so it looks like the bullet is deflecting to the right. Or curving to the right from the perspective of someone standing on the surface of the Earth. So the velocity that the bullet is traveling at is the square root of the sum of the squares of the velocity, the 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 muzzle velocity of the bullet going north to south. That's its north-south component, but there's also this little lateral component that's added to it. So it's actually 500 squared, the square root of 500 squared plus 8 squared, which is essentially 500 squared. But it wouldn't be if the bullet was, traveling much slower, where the component, north-south component, was starting to get closer to the lateral component. Then you have to use the more precise speed of the bullet relative to the surface of the Earth. You see what I'm getting at?
I'm not using muzzle velocity. I'm using the average velocity to get the time. Would
Average
this make a
velocity of
difference?
what?
Average velocity of the bullet.
But how do you know what that is?
Uh, uh, from the time of travel and some. Well, that's why I needed Fletcher in this conversation, because
Well, no, the muzzle velocities of rifles are typically somewhere around 2,500 feet per second for a rifle.
in meters, please.
Well, let's see here, 2,500 feet. So that's that's 0.47 miles per second. So in terms of kilometers,
No, I think that's too
that's
much.
1.6 09344 is a conversion. Wait a minute. What did I
That would
say?
be a railgun.
No, 2,500 feet per second is typical for a rifle, a high-speed rifle.
Okay, 3,000 feet is around 1 kilometer, right? So we're talking about like 600 or 700 meters per second.
Is that you or me?
Not sure. I don't know.
Hello? Oh, it's Dean. I'm sorry. That I guess no. Oh yeah, he was calling me. Hang on a second.
Okay.
Okay, we're back at 2,500 feet per second. Is roughly there's 40 inches roughly in a meter. So 39.37. Okay, I'll go a little more exact here. The 39.37 inches per meter divided by 12. So we got 3.1142 feet in a meter. So if I divide, we're looking at about 80.23 meters per second.
That's a little bit slow.
Or
Okay,
no, 802. I'm sorry, 800. Okay, I read it wrong. 802.
Okay,
Point
so
78 meters per second is 2,500 feet per second.
okay, so now I think it's time to ask a question. Does it matter what speed the bullets start and end with, or what matters is the time that it takes to reach the target?
The important thing in computing Coriolis deflection is time in flight.
Okay, so then this is what I should be.
I'm sorry, both velocity and time in flight overall is what determines how much deflection there is. But how much deflection, of course, depends on the velocity, because if you're traveling very, very fast, there's going to be little deflection because the tangential component contributes little to the bullet. So, what's important is both the bullet speed and the time in flight.
But the time is I mean, if
Well, what
if
determines the time is your range divided by the velocity, right?
the average velocity.
Well, velocity.
Because
You're assuming there's no drag, so the velocity doesn't change.
Yes, in this one, I'm assuming there's no drag.
Yeah, so the velocity does not change.
Yes, the velocity will control the time, and then the time will determine how many seconds had passed to get the total lateral shift.
So let's use realistic numbers here, Khaled. Let's say the bullet is going at 800 meters per second.
Continue constant speed.
Well, yes, I said
Okay.
It doesn't change. There's no drag.
Okay, so 800.
Yeah, 800 meters per second.
The travel time for that 1 kilometer will be 1 second and a quarter of a second.
Just a minute. 3.28, 39. Okay, so the conversions we're going to be using on is 3.208 that's feet per meter. There's 39.37 inches in a meter. And divide by 12, that gives you 3.2808. And if I multiply that by 800.
Hold on. You don't have to convert because I'm using metrics here. So
Yes, but I need to,
okay.
because I know a lot of these things in English units. So basically, what we're looking at is a bullet that's traveling at 2,624 or 25 feet per second. And that's realistic for a high-speed bullet. Okay.
Okay.
So that's a good number. Okay, so we have 800 meters per second. That's muzzle velocity. So the actual so that velocity isn't going to change. There's no drag. Your range is what, 1 kilometer, you said?
Yes, 1 kilometer.
Okay, so we've got 1,000 meters. And we divide by 800, and we get 1.125 seconds time for travel. 1.25 seconds, okay? All right,
Okay.
fine. Now, you have a tangential velocity difference between your two tangential velocities. So in the first case, 464.6, I take the cosine. So we've got 8.108 meters per second. And in the final one, I'm just re-verifying everything, 464.6. And we have a range of, what was that, 89? The stopping is at what latitude was it? 89 what?
The stopping is 88.99.
Okay, 88.91. Okay, 88.91. Cosine. So that's okay, so 88.991 multiply. So I get 8.8 or 8.181 meters per second.
Yes, that's what I have also.
Okay. And we subtract off our 8.1084. Subtract. So our change in tangential velocities is 0.0726 roughly.
That's almost exactly what I have. I have 0.073.
Okay, good. All right, fine. Okay, so flight time is 1.25 seconds. So we multiply that by 1.25 to get how much lateral deflection there is over that flight time. So
Yes.
we get 0.0908 roughly meters.
That's exactly what I have.
Or 9 centimeters. 9.08 centimeters.
9 centimeter, yeah.
Okay, so that's how much the bullet will have appeared to lag behind the surface of the Earth. It will have deflected about 9 centimeters to the right of the target.
Yes. I also added a cool feature here, which is the shooting angle.
Okay. That
So
complicates things
if
because now you have a parabolic trajectory.
no, I don't mean the vertical angle. I mean shooting west or shooting east, shooting south, the azimuth of shooting.
Dean keeps asking me questions. Should we want to invite him in here? He wants to
Yeah,
ask
sure.
something about centrifugal force. I don't know.
Okay.
It might
Send
not
him
be
the link,
related to
or I
this
can
at
send
all.
him now.
Apparently, you're not live, are you? This is just private hangout right now, correct?
Uh,
You're not streaming, right?
it's live on YouTube.
Oh, is it? Well, Dean says
I think I'm.
didn't find it on your channel.
Yeah, because this is a different. This is a different one.
Oh,
I'll send him the link.
okay. I'll tell him. While you're doing that, I'm just going to refill my drink. I'll be right back.
Okay.
Yeah, you kind
Oh,
of
welcome,
have
Dean.
to excuse me, Khaled, because I'm not really on the top of my game today. I had a rough night. It was so hot trying to sleep, and I did not sleep well.
It's okay. We did pretty well reviewing some numbers.
Oh, hi there, Dean.
This is actually slightly related to what you guys are doing, but just
Yeah. What
but-
is it about centrifugal force?
right. So I have 2 points on the planet, and I've got the latitudes. I want to calculate the Newton force difference, but I've got too many variables.
Okay. Yeah, that's easy to do. That is related to this. You see Khaled's screen there?
Yeah. Wait a minute. I'm going to put this in the side chat. These are my two locations. This is my two data sets.
Oh God! Now you're gonna make me open up side chat. Jesus. Oh, where is it? I hate this new.
Oh, well, I can put it in Skype for you if you want, George. So you don't have to do that if you want.
Well, just a minute. I'm trying to find. Where is it? Oh, there.
So there you go, Khaled. I've got two.
That's screen share. Shit! I hit the wrong damn thing.
I've got two data sets,
They
Khaled.
keep changing things here. Where's to open up the chat on this thing? Oh, there it is. Okay, I got it now. I'm in chat. All right. Okay, you've got. Okay, 100 grams. What's this 29.9 thing?
That's right. So the thing there is, I need the degrees to the force normal, don't I?
Well, I don't know. What does that number represent? I don't know. What is that number?
Well, we're spinning, and the normal.
I'm asking you, what are the units on that number?
degrees.
That's all.
Degrees.
I just want to know what is that.
Degrees.
Oh, Okay, that's a that's a latitude.
Oh no, so yeah. That's it.
Okay, that's a
Yeah.
latitude number,
It is. It
29.98
is indeed.
degrees
It is
north
indeed.
lat. Okay,
Yes. And then
all
it's
right, got it.
51 point.
Okay, all right,
And
got it.
and Khaled should actually recognize that latitude
Yeah.
as well.
Well, all you need to know in doing this sort of thing is that um uh, my my head's
That's
not.
in Egypt. Is that Todi
It is.
observation?
It is indeed. So the problem with this,
Okay.
Khaled, is I've done these calculations and I come out with the grams at the bottom, the grams difference from Newton
Okay,
force, but
all right.
that's wrong. And I think
Well,
it's wrong because the force
Dean,
normal. Yeah, go for it.
no, Dean. Okay, the central. What you're computing is what you need is this what we call the centripetal acceleration. Okay,
Mhm.
that's the surface, or that's the normal to the center of the Earth, which is also going to be the same as the centrifugal acceleration that's trying to pull you away from the Earth. Okay, and making your weight lighter.
Yeah, so
That's what you're looking for, right? Is how much of a weight reduction there's going to be due to the spin on the Earth at any given point.
yes.
Okay, so the centripetal acceleration is omega squared r, where r is the radial distance from the axis of the Earth to the surface of the Earth, not the center of the Earth, but the axis of the Earth. Okay. And
Yeah.
that's shortened by your latitude. And the way that it's shortened by the amount of the cosine of your latitude angle. So the r vector, the length of the vector, r vector, radial vector that you need is the radius of the Earth times the cosine of the latitude. So if you take the radius of the Earth as being 3,000 or 6,371 kilometers, you multiply by the cosine of your latitude, then that gives you the radial vector that you need. So you'd take, 6,371 kilometers times the cosine of 29.98. Okay. So that's your R. Now you need to know your omega, the angular velocity of the Earth. That's constant for everybody on the surface of the Earth.
Mhm.
And what that number is that has to be expressed in radians per second. And the amount of radians you have for one revolution is 2 pi, which is, 360 degrees in radian measures. So you have 2 pi divided by the rotational period of the Earth. Well, the rotational period that you use, the actual rotational period is the sidereal day, not the solar day. Solar day is exactly 24 hours, but the sidereal day is 23 hours, 56 minutes, and 4 seconds, which works out to 86,164 seconds. So you take 2 pi, divide by 86,164 seconds, and the rotational speed, rotational angular velocity of the Earth is 72.92 microradians per second. Okay, that's the key number. We'll call this omega sub e. That is, the angular velocity of the Earth is 72.92 microradians per second, or 72.92 times 10 to the minus 6 radians per second. Okay. Now you multiply that. So you take that number, multiply the radius of the Earth, then that gives you the we're dealing with accelerations. I'm sorry. So now the acceleration is omega r squared. Or wait, what am I talking about here? Getting bugged up. Let's see. Tangential velocity omega squared. It's omega squared. Yeah, omega squared r. I'm sorry. The centripetal centripetal acceleration, which is the number you're going to be using, is omega squared times r. So omega squared is 72.92 times 10 to the minus 6 I square that, and I multiply by the radius of the Earth, which is 6,371 million meters. So what we get for the acceleration is 33.877 meters per second squared. That doesn't seem right. What the hell did I do wrong? That's not right. Let me redo this. 72.
Also, George, can I just ask a quick question about this?
I
Yeah.
have
So, sorry, go on, Callum.
I have a spreadsheet ready. I made like a few months ago, and if it coincides with your numbers or the experiment, then the spreadsheet is correct.
Yeah,
So,
but your spreadsheet will
says-
just be based off going backwards from like a reduction in speed, a reduction in weight at the equator, won't it? A fractional reduction.
Okay. No, my number is right here now. The
Okay.
omega squared r, this is at the equator. This is the centripetal acceleration at the equator. It's going to be 0.033877 meters per second squared, or let's just round it to 0.0339 meters per second squared. That's the acceleration. That operates in opposition to the gravitational acceleration. Remember, gravitational acceleration is 9.82
Yeah.
meters per second. So the difference is going to be about 291. That's the number I use. Let me just check this to make sure. 8.92 divide. Yeah, 289.9. About 290 is a good number to use. That's the difference
Yeah.
that you're going to have between the gravitational acceleration and the acceleration due to the rotation of the Earth that's going to try to throw you off the Earth. So all you have to do to get the weight at the equator is just take a person's weight, divide by 291 or 290, and that gives you the amount that the weight's going to be lessened by.
Right. Okay.
At the equator.
But my question here is that
but you adjust by the cosine of the latitude angle to get what it is at any given point on the Earth at any given latitude above the or below the equator. So in number one there, say you have 100 grams. So to get, you use that number 0.0339 meters per second squared. If you want to get it in newtons, you have to have the mass in kilograms. So it's 0.0339 times 0.1. So you have 2.90 or 2.29 millinewtons or thousandths of a newton. Or number one. So you're trying to use gram weight. You should call that gram weight, is to differentiate it from grams.
So wait a minute. So wait a minute. What Newton force did you get for number one?
I didn't hear. Let me get that then. So I got to take. So you have 0.1 grams, 0.0339, and then I've got to take, what's your latitude there? 29.98 cosine multiply. I get 2.94 or 0.00294.
Okay. Now,
that's kilograms. I'm sorry, kilograms. So to put it in grams, I would get 2.94 grams.
I'm just wondering why I got 2.297 then. Okay.
Well, let me recheck. So 0.0339.
Because these seemed wrong to me, and I also didn't see where You know what I mean by the force vector of the force.
Yes,
Force
yeah, I
being,
know what you're talking about. Yeah.
yeah. But that's accounted for by using cosine of the latitude, because at let's say 45 degrees, the force vector's going to be not straight up.
Yeah,
So
I
it's
didn't. Yeah, I didn't. Yeah, I didn't account. Yeah, if you're off the equator, I did
this is
not.
what's
I
this
did
is
not
what's
figure
confusing
the
me.
component. I did not figure the component directed to the center of the Earth.
Yeah.
So my number, I'll have to correct. Let me think about this a second. I've got to figure out how to correct for that. Yeah, what I was doing with the direct subtraction, that only holds for the equator.
Yeah. That's
So
what I
we got
thought.
to look at the component directed towards the center of the Earth. See, if you take the acceleration, which is 0.0339 meters per second,
Yeah.
and you multiply by your mass, which is 0.1 kilograms,
Mhm.
then that gives us the force in newtons directed towards the axis of the Earth, not towards the center of the Earth.
Yeah.
And now, if I go, yeah, we're going to use the same angle as the latitude. It turns out it's just parallel lines with a line that intersects. So the angles, they're what we call vertical angles, are the same. So again, I would multiply. Well, let me think here a second.
Wait a minute. Can I ask a question, Khaled? This calculator. Did you do this in this spreadsheet?
Yeah,
Oh,
I would take the
Khaled's on mute.
component. We got to multiply by the cosine of the latitude once more. So if I take,
The spreadsheet is not correct.
Right. Okay.
so if I go with 0.0339 meters per second, we multiply by 100 grams. And then we multiply again by the cosine of 29.98. So I'm getting 2.94.
Yeah, that's what you got the first time.
But
that's
wait, yeah. Oh, wait, no, that, and then I got to square that. I'm sorry. I got to take cosine again. Or what was that? 29.98 cosine multiply. I get 2.54.
Oh wow.
Hang on a second. I gotta let Con in. He's scratching at the door.
Well, Khaled, are you there? Hello.
What?
Oh yeah. This
Yeah.
this isn't right. This calculator that you built then.
Yes, there was some basic mistake, and also I didn't include the vertical component.
Yeah, this is what's confusing me, and I can't do these calculations, and I hate math, which is why I've come to either you, George, or Rumpus. Is yeah, everybody can work it out on the equator, and then we can, and then I find people using the curve, and the reduction on the equator, but I want to calculate it properly the other way. But obviously, I need an offset to the force vector to calculate it, because here in the UK, I'm at 51 degrees. So not only is my radius a lot less, I'm 51 degrees off that that force.
Directional force, yeah.
Yeah, and this is what I would have thought there'd have been a really easy online calculator for all of this, but there isn't.
Well, whatever force you get, multiply by cosine your latitude or sine your latitude. One of these. I'm not sure which one.
So does this actually correspond to what you and you and George have been talking about then, with the Coriolis effect then?
No, we were working on calculating how much the bullet would shift.
Okay.
Ah.
Hey, Dean, have you got pencil and paper?
I've got a digital pad with a digital pen.
Okay, well, either way, I mean, something that you can mark some notes down. Okay.
Yes.
The important thing to keep in track. Okay. Let's call omega sub v, you know, omega.
Mm-hmm.
Okay. That's the angular velocity of the Earth. That's measured in radians per second. And that number is 0.0339 meters per second squared.
Sorry, say that again. 0.0339, did you say?
Yes.
Yeah.
Okay. 33.9 milliradians per second or millimeters per second.
Yeah.
Okay. 0.0339. That's omega sub v. That's a key number. And where that comes from is that's 2 pi divided by the rotational period of the Earth.
Which
And
is
the
20,
rotational period of the Earth is
23.
86,120 or 164 seconds. 86,164 seconds is the rotational period of the Earth. So 2 pi divided by 86,164 seconds comes out to 0.0339 meters per second. Okay.
Mm-hmm.
Or not meter. God, what am I talking? Radians per second.
Yep.
Radians per second, not meters. I'm sorry. Okay. So rotational periods are either angular velocities are, rotations per second or meters per second, or not meters per second, but radians per second. Okay. So omega sub e is 0.0339 radians per second. The rotational period is 86,164 seconds.
Mm-hmm.
And that's where that comes from. That's 2 pi divided by 86,164. So that's radians per second. All right. Now, the centripetal acceleration called A sub E or A sub CE, which is the acceleration, centripetal acceleration at the equator. Okay. A subscript CE. And that is omega squared of the Earth times the radius of the Earth. Omega squared times the radius of the Earth. Well, the omega squared is 0.0339 squared, and you multiply by the radius of the Earth, which we'll use as 6,371,000 meters. Okay.
Mm-hmm.
So we're going to get this in meters per second squared. And if you multiply that out, the acceleration, let's go 0.0339 by 6,371. Or omega squared, I mean. Did I say omega squared?
Yeah.
Okay.
Omega squared times radius.
Right.
Yeah.
So I'm getting 0.0339. No, there's something wrong here. What did I do? That can't be right. That isn't right.
I am so glad this isn't easy.
Omega sub e, I'm still not quite woke up here. Omega sub e, the radial or angular velocity of the Earth, is going to be 2 pi divided by 86,164. So that's 72.92 microradians per second. Okay. 72.92 times 10 to the minus 6 radians per second. That's the rotational velocity of the Earth.
Mm-hmm.
Okay, now if we square that and multiply by 6,371 meters, So the acceleration, centripetal acceleration at the equator is 0.0339 meters per second squared.
Yeah, that's
Okay.
cool. Yeah.
Now, at any other point, we'll just call it A sub C versus A sub CE. So A sub C will be A sub CE times the cosine of the latitude angle. So we take the acceleration at the equator and multiply by the cosine of your latitude angle to get the effective centripetal acceleration at some latitude point. Now, to get the component that's directed towards the center of the Earth, this is directed towards
The axis. Yeah.
axis. Now, to get the component in the direction of the center, you multiply again by the cosine.
And that's it.
And that's it.
Huh.
So it's cosine squared times the acceleration at the equator. So in your case, in the first case, we'll use the acceleration at the equator, which is 0.0339. That's the starting point. We start at the equator. So to correct for some latitude other than the equator, like in the first case, 29.98, I take the cosine, multiply by 0.0, whoops, sorry. That was 29.98. Well, I'll use 2287. Take the cosine, I square the cosine, I multiply by 0.0339, I get 0.0254 kilogram, or
grams,
meters per second squared. That's the acceleration.
Yeah, I get that.
Okay, so if we multiply by 100 to get it in effective gram weight, it comes to 2.543. Okay, so rather than wait, no, that can't be right.
That's
no, that's
a lot.
not right.
Yeah.
No, that's not right. Something wrong here. I must have punched in something wrong. 2.98 cosine, I square that, multiply by 0.0339. Why is this not?
Do you want me to come back to you, George, when you've had a bit of sleep?
No, hang on a sec. I've got to figure.
I'm done with my spreadsheet, but I'm not sure.
We got to compare. Yeah, what got me buggered up is you're using grams, and we got to put this in relationship to. We got to take that number, divide by 9.82, which is the gravitational acceleration, in order to compare. What you're looking at is difference in forces. If we have force due to gravity, we have mass times little g, right? Now, if we take force due to, let's call spin, we have the mass times the centripetal acceleration times cosine squared of the latitude. And if we compare, guess where I'm getting buggered up. Why am I getting buggered up here? Something.
But wait a minute, Khaled's calculator presented it, but just without the Earth Earth center relationship. It just had the tangent force. So couldn't he just cosine the latitude squared again?
I did cosine the
Yeah.
latitude here.
Okay.
If you can see the equation here,
Yeah, yeah.
9.8 minus cosine. I think it's cosine the radians, because I put the angle here in degrees, and this thing only understand radians.
Yeah.
So I'm not sure. So it should be 0.01 gram difference.
Yeah, I'd want more decimal places than that, to be honest.
Only. So what the result was? What, 0.1 gram or 0.01 gram?
Oh, I can't remember. Wait a minute. I don't know. I didn't ask him. I said I wanted to work this out. I wanted not to have the results. I wanted to go with him with I wanted to get back to him with the definitive answer for what it should be based on these calculations.
Well, it all starts with a diagram. Just draw a diagram and you'll solve it. And this answer is not confirmed because maybe there's some mistakes along the way. And that what we were doing before you come. He was doing his calculations and confirming what it did is right or not.
Hmm. Well, let me go away and have a play with this. And I've actually got to go play some Beat Saber with my girlfriend.
Well, what I'm trying to do is understand what you're doing here. Your numbers are. Well, what's you
The only
got?
thing,
100 on the top one, number one, you got 100 grams, and then what's this below it? 5574495.
well, that was the meter radius at that point in latitude.
Oh, okay, I got you. Okay.
Yeah.
6371E3 times you're using 29.98. Yeah, 5. I get 55185.
Oh, right. Okay. Bollocks.
What are you using for radius of the Earth?
I don't know. I actually just there was a reference table that I could look up, which I found online, which just gave me this figure when I looked up 29.
I always use the mean radius of the Earth, which is 6371 kilometers.
Yeah, but
If I use that number, you should have 5518432.
okay.
For 29.982287 times 6371E3 multiply, you should have 5.5184 million meters. Okay.
Mm-hmm.
Okay, tangential velocity then, if I take that multiplied by the omega, which is 72.92 micro
Radians a
radians
second. Yeah.
per second. Ah, shit, it gave me an error. Damn it. What's going on here?
Well, on this, that's my second number anyway. I got 402.86
72.
meters per second.
Okay, I got 402.4.
Okay,
Using
so
your
yeah,
numbers.
yeah.
Okay.
Yeah.
Now, so if we take, you've got your acceleration directed towards the center of the Earth, which is should be omega squared of the Earth times the radius of the Earth times the cosine of the latitude angle squared. So you could take it as the radius of the Earth times omega of the Earth cosine of the latitude, that quantity squared. So that gives you a component directed towards the center of the Earth. And all you need to do is compare that to the gravitational constant, or the gravitational acceleration of 9.82. So if I take 72.92, square that, multiply by the radius of the Earth, I want to do that in kilometers. And oh God, omega squared 6 multiply.
I'll be muted for 5 minutes. I'll be back.
All right.
So in terms of meters per second squared, it again is 0.0339. That's at the equator. And then we take our latitude angle, which is 2998, 2287. And if I square that and multiply, the effective acceleration to the center of the Earth in your case is 0.0254. Almost the conversion number between centimeters and inches, 2.54. No significance, just a coincidence, just a comment. So this is meters per second squared. Okay, so at that position number 1, the effective value of acceleration that counters the acceleration due to gravity is 0.0254 meters per second squared. Okay, that's at 29.98 degrees. Now, if you want to get what the weight change is going to be, then you can just ratio that to the 9.82. So if I divide that by 9.82, we get 0.002588. So any weight that you have without the spin of the Earth.
Sorry, say that again. That was
0.002588.
Okay, cool.
So that's the ratio of the centripetal acceleration to the acceleration due to gravity. That's how much.
So yeah, so that's 0.25 grams then in my case.
Yeah, if you multiply by 100, then that's the weight reduction. That's the weight that is going to be reduced. That's the amount of weight reduction you're going to have.
That's cool. That's cool. This seems better now rather than my 294 bollocks to start off with.
Yeah. So all you have to do, the simple equation here, Dean, is that if you want to get it, just take radius of the Earth, square the angular velocity of the Earth, the omega sub e, and multiply by the square of the cosine of the latitude angle, and then divide by the gravitational acceleration g. So that gives you the ratio. So you take that times any weight, and then that gives you, what portion is due to the spin.
Okay, cool. I fucking hate math. I fucking hate equations, but I'm going to say thank you very much and let you get back to your working.
So on the second case, well, let's look at the second case here. Let's take
Yeah, I came up with something weird. Yeah, I got 0.213 grams.
So 0.0339. And I correct that for the latitude, which is 51.57055. And then I divide by 9.82, multiplied by 100, and I get 0.2146.
Oh, I got 2 point. Yeah, that's actually not that far away from what I got.
Right.
But fuck knows what I was doing.
And anyway, the long story short is you need an extremely sensitive scale to register these differences, you know.
Yeah. Oh, are we sure this is right? Because this doesn't look like what Toady got. Now thinking back, I'm gonna have to watch his. I'm gonna have to watch his video actually. Bollocks. I didn't want to look at his results.
Well, we could put it all into a simple equation here for you.
Yeah, and send me an Excel spreadsheet. So all I need to do is enter the two fucking things. That'd be awesome.
Well, here, hang on a second.
That would be
So we
awesome.
got mega square radius of the Earth cosine squared theta L1. So we're going to look at the differences. 2
I'm back.
by G times the weight. Yeah, so what you would do, I'll just confirm it here. 0.339. We got 2.98 or 29.98 cosine square that. And the other one is 51.57.055. Take that. Subtract them. Multiply 9.82, divide, and multiply by 100. I get 0.1256.
On what? What are we on about
That's
now?
the difference. That's the difference in weight. 0.125 grams, roughly.
Okay.
What did we have? We had, for the other one, it was like 0.25 something, wasn't it? 0.258, 8, and 0.245. Well, it'd probably be better not to do it all in one formula because it'd be better for you to have this in steps. So what I would say is do this, Dean, is you're going to first, well, I'll tell you what, let me write something up on a sheet. I'll scan it in and then I will post the file. How about that?
Yeah, that'd be cool. Right, actually, I'll let you and kind of get back
Yeah,
onto your.
I'll post it on your Skype.
Yeah,
Here,
that'd be cool.
yeah, when Khaled and I finish. Let me write your numbers down here quick before you go, because I'll work it out for you.
Oh, nice. Is that because you know I hate math?
I hate it. I don't like it when people say they hate math. Wouldn't it be better?
No. Sorry, I hate attempting to figure out math that I don't understand or have the time to learn properly. Because that's what I mean. I don't mean I hate math.
Yeah,
Math
yeah.
is fucking
Because
awesome,
that makes you
wondrous.
sound like that makes you sound like a flat earther.
Yeah. No, you know what I meant, George. I don't.
I know what you mean. I'm just being
Yeah,
Facetious.
not
Facetious is
rejecting
the word there, George.
yes.
No, disliking math is one thing, and rejecting math is right.
Yeah. No, I
Yeah.
dislike doing
Well,
math.
yeah. Well, what the
That's
hell are you doing this for anyway, Dean? Since when does this describe reality? It's math.
I know, right?
Jesus Christ. You know, this is all fantasy anyway.
Indeed.
I mean, since when do you live on a model?
You should be a flat earther, George. I'm telling you, you'd be really good at it.
Oh,
As-
I think we should continue this later because there's supposed to be someone on Ranty Flat Earth today, right now, who's going to make a counter video for the analemma that I made, and he's
Oh,
going.
wow.
Oh, yeah, that's important for you. Okay.
Yeah, so please go and watch it. Let's see what he's got to say.
Yeah. We'll catch up later. Cheers, George. And
Yeah.
thanks, Khaled.
Yeah, I can help you out later. Maybe I got you on the right path here, Khaled, anyway, on your sorry we got sidetracked here.
Yeah. Sorry again, guys. I'll speak to you later.
Yeah, that's okay. See you.
All right, go catch it. Why don't you just keep the hangout open here, or contact me with Skype when you're ready. Via
Yes,
Skype.
I'll close it for the
Sure.
internet.
Well, just destroy this hangout and we'll start over now that I'm awake.
Yeah. Okay.
Yeah, just totally disregard this past hour.
Okay.
All right, catch you later.
Catch.